According to Article 230.42 of the National Electrical Code, where there are no unbalanced loads, the size of the grounded conductor shall not be less than the required for the circuit conductor where the grounded conductor is not used to carry unbalanced load current. In a situation where all the loads are three-phase and there are no 277 volts loads, the load on the grounded conductor is theoretically zero, meaning that the grounded conductor size can be reduced. However, before reducing the size of the grounded conductor, there are several crucial factors that need to be taken into account. Firstly, the NEC itself does not explicitly specify the absolute minimum size of the grounded conductor that can be used in such a scenario. Therefore, it is essential to consult with the local authority having jurisdiction, often abbreviated as AHJ, to determine if there are any specific requirements or regulations that must be adhered to in that particular locale. Secondly, the size of the grounded conductor must be sufficient to handle any fault currents that may occur within the electrical system. Fault currents can be exceptionally high, and it is of paramount importance to ensure that the grounded conductor is adequately sized to safely and effectively carry these currents back to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. Thirdly, the grounded conductor must be properly bonded to the equipment grounding conductor at the service entrance. This requirement is stipulated in Article 250.24b of the NEC, and it is intended to establish a low impedance path for fault currents, ensuring the safety of personnel and equipment. After careful consideration of these factors, the appropriate size for the grounded conductor can be determined. It is important to reiterate that while the NEC permits the reduction of the grounded conductor size when there are no unbalanced loads, it does not provide a specific minimum size. This necessitates a thorough evaluation of the potential fault currents and consultation with the local AHJ to ensure compliance with all applicable codes and regulations. The primary function of the grounded conductor, also known as the neutral conductor in some contexts, is to provide a return path for unbalanced currents in a three-phase system or to carry current in a single-phase system. In a perfectly balanced three-phase system, the currents in each of the three phases are equal in magnitude and 120 degrees apart in phase angle. As a result, the neutral current is ideally zero. However, in real-world scenarios, perfectly balanced loads are rare, and there is typically some degree of imbalance. This imbalance can arise due to various factors, such as unequal loading on the phases, the presence of single-phase loads, or variations in the impedance of the phase conductors. In a system with significant unbalanced loads, the neutral conductor carries the difference between the currents in the phases, and it must be sized accordingly to prevent overheating and voltage drop. However, in a system where the loads are predominantly three-phase and balanced, the neutral current is minimal and the grounded conductor can be reduced in size as permitted by the NEC. It is important to note that the reduction in size should not compromise the safety or performance of the electrical system. The grounded conductor must still be capable of carrying any fault currents that may occur, and it must be properly bonded to the equipment grounding system to ensure a low impedance path for these currents. In addition to the NEC requirements, there may be local codes or regulations that impose additional restrictions on the size of the grounded conductor. It is always advisable to consult with the local AHJ to ensure compliance with all applicable codes and regulations. The process of determining the appropriate size for the grounded conductor involves several steps. Firstly, the maximum unbalanced load in the system must be calculated. This can be done by determining the difference between the currents in the phases under the most demanding operating conditions. Secondly, fault current carrying capacity of the grounded conductor must be evaluated. This involves calculating the maximum fault current that could flow through the grounded conductor in the event of a ground fault. The fault current carrying capacity of the grounded conductor must be sufficient to safely carry this current without overheating or causing damage to the conductor. Thirdly, the bonding requirements for the grounded conductor must be addressed. The grounded conductor must be properly bonded to the equipment grounding system at the service entrance and at other points as required by the NEC. This bonding ensures a low impedance path for fault currents and helps to prevent electric shock hazards. Once these factors have been considered, the appropriate size for the grounded conductor can be selected. It is important to use appropriately sized connectors and terminations for the grounded conductor to ensure reliable and safe electrical connection. In summary, the NEC permits the reduction of the grounded conductor size in systems where there are no unbalanced loads. However, this reduction must be done carefully and in accordance with all applicable codes and regulations. The grounded conductor must be sized to handle any fault currents that may occur, and it must be properly bonded to the equipment grounding system. Consulting with the local AHJ is essential to ensure compliance with all applicable requirements. The grounded conductor plays a critical role in the safety and performance of electrical systems, and it is important to understand the requirements for its sizing and installation. This specific article, 230.42, emphasizes the conditional allowance for reducing the grounded conductor size. The key phrase is where there are no unbalanced loads. This condition is rarely perfectly met in real-world installations, but in a system designed and operated with exclusively three-phase loads and no single-phase loads connected to the neutral, the potential for reducing the grounded conductor size exists. It is crucial to understand the distinction between a grounded conductor and an equipment grounding conductor. The grounded conductor, as discussed, carries neutral current under normal operating conditions even if minimally in a balanced system. The equipment grounding conductor, on the other hand, is intended to provide a low-impedance path for fault currents back to the source, thereby facilitating the operation of overcurrent protective devices and minimizing the risk of electric shock. The NEC mandates that the grounded conductor and the equipment grounding conductor be bonded together at the service entrance. This bonding is essential for creating a safe and effective grounding system. When considering reducing the size of the grounded conductor, it is imperative to ensure that the equipment grounding conductor is sized adequately to handle potential fault currents. The equipment grounding conductor size is typically determined based on the size of the overcurrent protective device protecting the circuit, as specified in NEC Table 250.122. Even if the grounded conductor is reduced in size, the equipment grounding conductor must still meet the requirements of this table. Furthermore, the NEC provides specific rules for the installation and bonding of grounding electrodes. Grounding electrodes are used to connect the electrical system to the earth, providing a path for fault currents to dissipate. The NEC specifies the types of grounding electrodes that are permitted, as well as the requirements for their installation and connection. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. The selection and installation of grounding electrodes must be done in accordance with the NEC to ensure a safe and effective grounding system. In addition to the NEC requirements, there may be local codes or regulations that impose additional restrictions on grounding practices. It is always advisable to consult with the local AHJ to ensure compliance with all applicable codes and regulations. Grounding is a critical aspect of electrical safety, and it is essential to understand the requirements for grounding conductors, equipment grounding conductors, and grounding electrodes. Proper grounding practices help to minimize the risk of electric shock, prevent equipment damage, and ensure the safe and reliable operation of electrical systems. The concept of fault current is also of utmost importance. Fault current is the current that flows in an electrical circuit during a short circuit or ground fault condition. Fault currents can be very high, often thousands of amps, and they can cause significant damage to equipment and pose a serious risk of electric shock. The NEC requires that electrical systems be designed to withstand the effects of fault currents. This includes selecting overcurrent protective devices that are capable of interrupting the fault current, as well as ensuring that conductors and equipment are adequately sized to handle the fault current without overheating or causing damage. The calculation of fault current is a complex process that involves considering the impedance of the various components in the electrical system, including the source impedance, the conductor impedance, and the equipment impedance. There are several methods for calculating fault current, including the point-to-point method and the impedance method. Choice of method depends on the complexity of the electrical system and the level of accuracy required. Once the fault current has been calculated, it is important to select overcurrent protective devices that are capable of interrupting the fault current. Overcurrent protective devices, such as circuit breakers and fuses, are designed to automatically interrupt the flow of current in a circuit when the current exceeds a predetermined level. The interrupting rating of an overcurrent protective device is the maximum fault current that the device can safely interrupt. The interrupting rating of the overcurrent protective device must be greater than or equal to the calculated fault current at the point where the device is installed. In addition to selecting overcurrent protective devices with adequate interrupting ratings, it is also important to ensure that conductors and equipment are adequately sized to handle the fault current without overheating or causing damage. The NEC provides specific requirements for conductor sizing and equipment selection based on the calculated fault current. It is essential to follow these requirements to ensure the safety and reliability of the electrical system. Fault current protection is a critical aspect to electrical safety, and it is important to understand the principles of fault current calculation, overcurrent protection, and conductor sizing. Proper fault current protection helps to minimize the risk of electric shock, prevent equipment damage, and ensure the safe and reliable operation of electrical systems. In the context of reducing the grounded conductor size, the potential impact on fault current flow and protection must be carefully considered. While the grounded conductor may not carry significant current under normal operating conditions in a balanced three-phase system, it can play a role in carrying fault current during a ground fault condition. Therefore, reducing the size of the grounded conductor could potentially affect the impedance of the fault current path and the performance of overcurrent protective devices. It is important to evaluate these potential impacts before making any changes to the grounded conductor size. Furthermore, the NEC requires that electrical systems be designed to provide a low impedance path for fault currents back to the source. This low impedance path is essential for ensuring that overcurrent protective devices operate quickly and effectively to clear the fault. Reducing the size of the grounded conductor could potentially increase the impedance of the fault current path, which could slow down the operation of overcurrent protective devices and increase the risk of damage to equipment and electric shock. Therefore, it is important to carefully evaluate the impact of any changes to the grounded conductor size on the impedance of the fault current path. In addition to the technical considerations discussed above, it is also important to consider the practical aspects of reducing the grounded conductor size. For example, it may be difficult to physically install a smaller grounded conductor in existing equipment or raceways. It may also be difficult to properly terminate a smaller grounded conductor in existing connectors or terminals. These practical considerations should be taken into account when evaluating the feasibility of reducing the grounded conductor size. Furthermore, it is important to document any changes that are made to the grounded conductor size. This documentation should include the calculations that were performed to determine the appropriate size of the grounded conductor, as well as the reasons for making the change. This documentation can be helpful for future maintenance and troubleshooting. In summary, reducing the grounded conductor size in a balanced three-phase system is possible under certain conditions, but it is important to carefully consider all of the potential impacts on safety, performance, and practicality. The NEC provides specific requirements for grounding conductors, equipment grounding conductors, and fault current protection, and it is essential to follow these requirements to ensure the safe and reliable operation of electrical systems. Consulting with the local AHJ is also advisable to ensure compliance with all applicable codes and regulations. Ultimately, the decision of whether or not to reduce the grounded conductor size should be based on a thorough evaluation of all of the relevant factors. The information provided here is for general guidance only and should not be considered a substitute for professional engineering advice. A qualified electrical engineer should be consulted before making any changes to the electrical system. The NEC is a comprehensive document that covers a wide range of electrical safety topics. It is important to stay up to date on the latest edition of the NEC and to understand the requirements that apply to your specific situation. The NEC is available for purchase from the National Fire Protection Association, as well as from other sources. In addition to the NEC, there may be other codes or standards that apply to electrical installations in your area. It is important to be aware of these other codes and standards and to comply with them as well. Local codes and standards may be more stringent than the NEC in some cases. Electrical safety is a shared responsibility. Everyone who works with or around electricity has a responsibility to follow safe work practices and to be aware of the potential hazards. By working together, we can create a safer electrical environment for everyone. The NEC Article 230 covers services, which is the connection between the utility company's distribution system and the building's electrical system. 230.42 specifically addresses the size and rating of service entrance conductors. Subsection C focuses on situations where the load characteristics allow for a reduction in the grounded conductor size. However, it's crucial to remember that this is a conditional allowance, not a blanket permission. Before making any changes, several factors must be meticulously assessed. Firstly, the no unbalanced loads condition must be strictly met. This means that the vast majority, if not all, of the connected loads must be three-phase. Single-phase loads connected line to neutral will introduce current on the grounded conductor, negating the possibility of reduction. Secondly, even with balanced three-phase loads, harmonic currents can circulate in the grounded conductor. Harmonic currents are generated by nonlinear loads such as variable frequency drives and electronic power supplies. These currents can add up in the neutral even if the fundamental frequency currents are balanced. Therefore, it's necessary to assess the presence and magnitude of harmonic currents before reducing the grounded conductor. Thirdly, the reduced grounded conductor must still be adequately sized to handle any ground fault currents. The ground fault current path includes the grounded conductor, and its impedance affects the magnitude of the fault current and the speed of operation of the overcurrent protective devices. A smaller grounded conductor will increase the impedance of the fault current path, potentially reducing the effectiveness of the protection. Fourthly, local regulations and the AHA may have specific requirements regarding the minimum size of the grounded conductor, regardless of the load characteristics. It's essential to consult with the AHA to ensure compliance with all applicable codes. To properly size the reduced grounded conductor, several calculations may be necessary. Firstly, a load calculation should be performed to determine the maximum unbalanced load in the system. This calculation should consider all connected loads, including any future loads that may be added. Secondly, a fault current study should be performed to determine the maximum ground fault current that could flow through the grounded conductor. This study should consider the impedance of the source, the conductors, and the equipment. Thirdly, the grounded conductor should be sized to meet the requirements of NEC Table 250.122, which specifies the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device. The grounded conductor should be at least as large as the required equipment grounding conductor. In addition to these calculations, it's also important to consider the voltage drop in the grounded conductor. Excessive voltage drop can cause problems with equipment operation and can also increase the risk of electric shock. The voltage drop in the grounded conductor should be limited to a reasonable value, typically 3% or less. The decision to reduce the grounded conductor size should not be taken lightly. It's a complex issue that requires careful consideration of several factors. It's always best to consult with a qualified electrical engineer before making any changes to the electrical system.